AC power. Most of the experiment is done with 120 volts. Turn this off, so that says 120. What's the first question?
Measure AC volts, amps, and power.
This will measure amps, volts, watts. So what was the first question you needed to answer? Is there a question from kind? Calculate peak voltage. How do we know peak voltage is? Put your finger on it, measure it.
Touch with your tongue.
Touching is good.
Use a
Tongue?
meter.
It works for maybe up to 9 volts. I wouldn't recommend it beyond 9 volts DC. Okay? So if I plug something into this outlet, we should be able to find out what the peak voltage is by looking on the scope. You need a cable. How about this one? Could we use this one to measure power line voltage? This is 50 volts per division. Is that a good number? So how many do we think is the peak value? What do you calculate?
170.
170? So if it starts at 0 here, 50, 150, 200, should be on range, should be about right. It assumes you have a 10-inch probe, so I can't use this, can I? If I change to a 1-inch probe, the maximum I can get is 5 volts per division. I can't measure a big voltage with this. So I need a 10-inch probe. So it says 10-inch probe, let's plug in the 10-inch probe. It's not your turn, it's your turn. Could you set this to 10x setting, please? Okay, so now we can change this back to 50 division. And if I plug this thing in, and you don't touch, but I touch, this is a demonstration, right? You're not going to get hurt. If I go up in smoke, then you can say you passed. All right, so I'm going to plug this thing in, and we're going to touch one of those 2 wires. And see if we can find out what the magnitude is. Okay, that's good now. It's on 50 per division. Yeah, it doesn't go good. But this one. I think we found it. Okay, go. What do you think? What should it be? 170 you calculated?
Yes.
50, 150. And so there's 5 little ones in this, probably 10 each. So 160, maybe close to 170.
That looks right.
You said you're not throwing it correctly, and so we got the right value.
Sign.
So that's the first thing. We calculated, we generated, we verified it. Someone else generated, we verified it. What's the next one? Volts DC equivalent to 4.5 volts peak.
Look at the pre-lab.
We're
Yeah,
gonna
we're also
verify this
verify.
stuff. We calculate it and then we come back and try it. So, what is the DC equivalent of 4.5 volts? How can we verify that? One way I propose is to have a little lamp and drive it with approximately 4.5 volts peak sine wave and see how bright it is, and then switch to DC and adjust the DC until we get the same intensity. If it's a hot filament type bulb, not an LED and not a fluorescent type whatever, it just takes just a hot wire type thing. Then it should respond to RMS some way, and then to DC it should respond some way, and we'll find out if the numbers correspond. So I've got that set up over here. Take a look. It's kind of complicated, but I'll explain it to be really easy. I made it so someone else could run this besides me. That's your turn?
Yeah.
Your turn. You get to verify something, and then other people are going to help you. You can't do it by yourself. All right, so I have This thing plugged in over there, and when I turn it on, I get a light on, I get my DC. When I go here, I've got AC, DC is adjustable. It's AC adjustable. Over here, it's on. It's DC, which is adjustable right there. And I made it so you cannot get too much DC and turn up the bulb. How much voltage RMS is this 4.5 volts? 3.1?
3.18.
About 3.1. Well, this bulb is rated at about 3 volts, and I don't want to risk burning it out, so I'm not going to let you change it above 3 volts. We're going to stick with a little bit under 3 volts, so that's longer. It's on the same intensity with both. Okay, so we need a volunteer. Over 2.
Yeah.
To come with you. I'll move back, moving your chairs over. One gets this job. All right. The other one turns back. Okay. So bring your chair, because you'll be here for a while doing this. And the other person gets to turn back. Hey, bring your chair, because you're gonna. Two chairs. You don't stand there, right? You're in the way, so you can't do that. He's over there reaching this. That's all. One is rotating it out, he's there. And we'll then make our measurements later. So for now, the job is just push it.
You guys give me your opinions of intensity? A little more where? Right now? Yeah, keep going bright.
You think you back on it?
About there.
Okay.
So we got 2 points,
Don't touch these, they touch back.
we got 2.8 volts DC, and then on the AC, looking at 2.84.
So 2.84 versus
2.79 something.
Can you get any closer than that?
Probably.
How would you
They're
get it
probably
closer?
on
Put it,
How do you know how bright it is?
put it, measure on DC. Measure it, actually.
Let's do that. We have a little wedge right here for doing that. Let's get a better measurement. This is pretty good. Now, let's see what this does. We turn this on. If we're gonna head over here, it's less or more. I think if we use this one, we can get a better measurement.
Absolutely.
We found it?
Yeah, I think
Now
I'm
let's
okay.
measure the voltages. What are they? What's the AC?
2.8.
2.856?
Power.
Switch here.
That's
And
2.846.
so 2.85 roughly, and
Looks like we're about
2.85 roughly? Yeah.
Well, 2.86, and
Okay,
then
2.86, 2.85?
We've got 100 discrepancy. I don't know what we're gonna do about that.
So what does that
Lux
tell you about
meter.
RMS
0.01,
and DC?
oops, sorry. They're definitely
Yep. Okay, for a hot resistor, the light, it responds the same to the RMS number. Do we believe this meter? Look what it says about the RMS number. What does it say on top?
true or, oh,
True RMS.
yeah.
Those Harbor Freight meters you've been using, they were false RMS, but they don't advertise that. This one brags. True RMS. They'll look that say. So we trust this meter. I trust you did it right. That's about as good as I know how to do it. Well, next question. IRMS for the following loads, given 120 volt supply. So if we need to adjust 120, you'll do that?
Yeah.
It might change a little bit depending on the load we get. So change a little bit. Could be inaccurate if we try to maintain. All right, incandescent bulb rated at 100 watts. Here's one of those. Let's see, who needs a job? Because you've had a job.
Yeah.
You've had a job, me a job. A bulb like this, could that be the kind that's mentioned in the question we're talking about?
100 watts? Yeah.
100 watts, 120 volts? Okay, that looks good. So we could measure on this thing and find out, what was it, down current?
Yes.
I'm inserting one more thing that's not in the instructions, but it's kind of fun to do. What is the resistance of this bulb
It's pure resistance.
when it's running, under the normal conditions? Let's see, power is volts times amps. Forget the cosine because it's hot wire, there's no reactive, okay? So power is volts times amps, also
V
volts
squared
squared
divided by power.
divided by your resistance.
V squared divided by power equals
Square.
44.
144 ohms, I believe you. Okay,
No.
Yeah.
you don't believe that? Let's use this non-true RMS meter. I think it's good enough for ohms.
P squared over P.
And let's measure the resistance. What do you think it should be? I'll hold the bulb, put this thing on ohms, there's the ohms. Put the leads together, see if it goes to 0. Yeah, make it good. 0.1, 0.3, so it's reasonably close. And you're hoping to measure 144, so make one a good connection on the side and one a good connection on the end. Poke it, stab it, whatever it takes.
Touch it with your tongue.
And assuming it had 0.3 in the first place, it's around 9 ohms. What happened to 144? It's not running. Oh, when it gets hot, the resistance changes. Okay, so once the resistance changes, then we're going to have the amps you calculated, hopefully. What did you calculate?
It's
0.83 amps.
0.83, well, let's try it out. Little wattmeter over here, and we're gonna plug a similar bulb. I'm not tricking you, does this work like the same bulb? Same kind of bulb? I have a spare in case we drop it. Looks like the same bulb, doesn't it?
Yeah.
I think it is, okay. We're gonna plug this thing in.
I can only tell if I lick it.
Now I need somebody else to verify how this equipment is connected as near as you can. And this is measuring the voltage across a small resistor. The resistor is connected on the ground side of the power line. And by observing the voltage across the known resistance, we can see the wave shape of the current. If I'm going to verify the current waveform relative to the voltage waveform, I need a reference. Who's this thing? Trigger menu, I'm using the AC power line as my reference. So the reference is power line voltage. And we're going to observe the wave shape of the current. Now to find out if it's working right, we need to plug in something which is purely resistive, such as the light bulb. And this is 100 watt bulb. Okay, watts. That's about 100 watt bulb. And look at the wave shape over here. You know, I'm working right all the time to keep this. Hey, there's one volt. Yeah, I got it there. That's the current. You should agree with the voltage waveform. So what we're seeing now is a reference. We're letting 0 be right there in the middle. I'm going to turn on the cursors. And this main reference is right through the center. That's where 0 degrees will be. What happens if I plug in a capacitive device or a reactive, conductive device? Well, let's see if that will actually work that way. Try something. Plug this in. According to my measurements, this is about a 7 microfarad capacitor, and whatever else it used to be is thrown away. That's all I'm saying. I'm protecting myself against getting touched, touching the voltage. But it should be a capacitor. What do you expect the waveform should do? If that's really a current waveform, and is right in the center is the reference, what should the current do? Shift right, shift left, shift up? Passive. The
Leads.
it should shift left, apart.
Shift right.
17 degrees? 120 degrees? What? How about 90 degrees?
That's one of my questions.
Should, Oh, they don't know? They did phasers and they don't know?
Oh, yeah, 90, yeah. 90 degrees.
Should be 90, okay? So plug it in, we'll see. Does it look shifted?
Yeah.
See, now, it's at its maximum, where the other has 0 degrees. So it must be about a 90 degrees phase shift. Sorry, it looks a little weird, can't help that part. That's what it looks like. So the angle has been shifted. So instead of rising right here in the center, it's rising earlier. The current is leading the voltage. I think we have a reasonable piece of equipment here for measuring the angle. You know, use cursors to figure out the angle by here. With their help.
Yeah.
Yes. All right, so there I've got the fine line and the thick line. One goes on 0, the other one is over there where it's about crossing 0 now. And if I look right here, it looks like 3.8 milliseconds. Can you have somebody help you and calculate that in degrees, unless you want to do it?
Do you have your calculator? Do you need that from them?
Delegated.
3 milliseconds.
3.8 milliseconds, that's a small amount of time. What's the large amount of time? Is it 60 hertz? We trust the Rocky Mountain Power is doing 60 hertz?
Yes.
Custom troubleshooting comes 3 seconds.
So what is the angle now?
82. Pretty close. And that could be just
So
a
it
function
could
of
be, I didn't set the
milliseconds.
cursor quite right. So within experimental error, we got our 90 degrees phase shift.
Yeah.
If maybe you did it, we'd get a better number, but I didn't. Okay, we have 90 degrees, 90 degrees. So plug the light bulb back in, it should be back to 0, shouldn't it? How's that? About 0? It works. All right. What did it ask for next? Anything doesn't matter. We didn't ever measure the amps, did we? Plug the lamp back in again. Amps. How do you get the inside of this thing? Push the amps button. I'll do it. I'm close.
All right.
How do we know if it's 0.83 or not?
It's close.
We can't tell with this one, it only has one digit showing. It's got 0.8.
Close enough, right?
Close enough? Call that good?
Yeah.
Okay. 136 watts. I don't have a bulb of that size. It's not standard, is it? I don't have a bulb of that size. But you still calculate the current, didn't you? What current do you expect?
1.13.
How much?
1.13.
1.13? So if you measure current on such a thing, it might say 1.1?
Yeah.
All right, we'll come back to that.
Oh, can't we just, because it,
All right, a motor, inductor. I've got 2 fans here which behave like the motor just being described in here. So, this time I'm going to use this strip so that I can plug in the 2 motor connections. So how to plug it in front. If I plug it in the back, somebody can't see it, they won't trust it. Once the fan is on, you'll see if it's still on. Why not? Not your fault. Wait, put the fan in. Plug this one in. Plug that one in. Turn it on. And 120 now? What about the angle? This is partly inductive. See where 0 is? It moved, didn't it? We got 120, that's good. How much current might it be taking? Should we verify the power factor?
Yes.
Probably.
How do we do that?
We can.
Calculate the
look at
angle.
the angles. You can just look at the angle of the current. And
Let's see, who had a job before? How do we know if we got the right power factor? What will it look like? Would you please calculate that?
What
How
was,
much time
okay,
would
what
it
was
take?
the angle?
49.98.
Roughly 50 degrees. So if you did have that power factor of 0.643, 2.3 milliseconds, well, let's see if we can get that. HDD, okay, so we have 2.5 milliseconds. Two point 5 milliseconds, how close is that to the
First
power
time.
factor?
2.3 is what we had.
2.3,
So 2.3 should have been 2.5, around there?
or it should have
Okay,
been.
so the current might actually be close too. How much current did you calculate?
0.8, or no?
Let's see.
You're doing 136 volts.
No, we're talking about the fan, the
1.76.
motor,
Yeah.
the inductor.
1.76.
1.76.
The watts is a little bit out too, instead of 136, I got 130. The volts is still there, isn't it? 120.
Oh. Jackie. Jackie.
Slightly. Watts? We have 129, sorry, it's not 136.
Wow, bummer.
Well, what should the current be?
1.76.
You've got a little bit.
1.76?
Yeah.
So it might be slightly,
Current will be slightly lower.
Slightly low.
1.76 to the first digit, we 1.8. So it looks like we verified the current, and the angle, the fan,
Mm-hmm.
it works.
Nice work.
Now, how about a capacitor now? 40 microfarad capacitor. What would that look like? Not this one, it's too small.
That's why you're gonna get,
Roughly looks like that.
if you do that, it's gonna get the power factor that you want.
Maybe.
I mean,
So we're gonna try a capacitor, and,
isn't that what we calculated?
well, in part, we're still using one capacitor, but not with an motor.
Why you don't highlight that? And so I missed that one. Calm down.
Okay, now plug in this capacitor. Now, I do this part, and you don't do this because we got some exposed wires there. And you don't have to do this.
Thank you.
So that was 30.48, and that was 120 volts change. What was that number? That was Q.
Yeah, it's not moving.
And the angle was pretty close to.
Just capacitor. What about the angle? Looks like the 90 degrees.
The angle looks like.
We expected a 90.
Yeah.
How about the current? Oh, the voltage is off. You turn the voltage back to 120. You got a jump for it, don't you?
The only one that's been hired on for the whole class period.
You better start paying attention.
He's observing. Okay, so we got 120. How many amps should it be?
1.8.
1.8.
Well, no, we could, with the capacitor in place,
No, just the capacitor by itself.
just the capacitor by itself. Was that, I didn't.
That was
The
part 3D.
1.38.
Calculate the IRMS for the following loads. We got the 120, we perfect those.
1.8.
And 40 microfarads, what's the current supposed to be?
1.8.
1.8?
Hey-o.
Close enough?
It's pretty close to 1.8.
It says 1.8. We'll call that good enough? These people need something to do. Okay, one of you three, come on over, one of you three that haven't done anything yet, come on over here. I want you to measure the watts. If you touch it, you let me know.
No,
Do not do this at home. Watts, we're about to measure watts. Come on, push the button. Now, maybe we can get a better guess by you pushing the button.
He got it. You nailed it.
Did I say 0 right?
Huh?
There we
Push
go.
the button, and see what's next. Don't push so hard, they cut back.
You nailed it.
0 watts?
0 watts.
0 watts.
Is there no current? Look at that, there's current. Look, there's amps. Oh, there's voltage too, right there. And you're at the short 120. See, we're done. You don't think there's any voltage on it? How much voltage was on there when I pulled it out?
120.
When you pulled it out, for a couple of milliseconds, there were probably 100 and, well.
We don't know, because we don't know where the power line was when I pulled it out. How do we find out? Don't put your tongue. There wasn't anything. Let's try it again. Wasn't 0, was it?
No.
Sometimes it's the bigger part. All right. So we're ready for the next part. 120 volt, RMS motor, 1.8 amps, lagging by 50. So is this fan going to be qualified for that condition, close enough, you think?
Oh, that's
Well,
right.
it was supposed to be 50 degrees, and we didn't have 2.3 milliseconds, so the angle is a little off, pretty close. And 1.8 amps, we saw that. 60 hertz, 120, we always get the one. How much capacity should we need? Everyone should calculate this.
30.5.
Okay, so if I put in this 40, it'll be too big. What will it do? Instead of getting 0, which is what the lamp will get, and instead of lagging, which is what the fan will do by itself, it would lead a little bit, wouldn't it? It's too big. Right. I'll plug it in, that, because wires are exposed. All right. So there's lagging. Plug this in, it should be slightly leaking. A little hard to tell, but it's probably slightly leaking.
Yeah.
I think they don't believe it. They're not believe it. I don't believe it. Take up capacitor, is it blank? What we need is a smaller capacitor. Electrically small, not necessarily physically small. And this one is it.
Oh, lagging, so there it is. That's
Something measured.
Yeah, so.
So the reason that this one is physically larger than that one, this is rated at a lower voltage. Should be rated at a larger voltage, it requires more.
Let's see what
This one is a smaller capacitance value, it might be right. Please go back and look and see if it's a little better.
Oh my God.
Wrong. There's. So the IRMS was higher, 1.8, and when we connect the right side capacitor, it went down to what, 0?
The IRMS?
Yeah. Would it go down to 0 if we do this power factor correction? We correct it, make it 0 power?
The imaginary component of it.
Okay, but there's still a resistive component to it. Okay. What will the current go down to?
1.16.
One more time.
1.16.
Turn it on, and then push the gas button. Don't touch these wires. It did go down. It did go down. Look at the magnitude of the current waveform. If I take the capacitor out, it's going to be changing and going to be larger. Faster help. You believe it? Convince them.
So we have this prior to the results of.
That's
Not
what Harvey said.
Right here, I think.
Harvey said it.
Determine how a hairdryer's low setting is accomplished. What wave shape does the current become in low setting? How is this done?
For a hairdryer.
Hairdryer.
Oh, that's one more thing. Just observation.
Times 120. And then divide that by sine 50.
We have here a hairdryer, thingy, top part was. That's the sine wave.
So do the.
And then that's half a sine wave.
Why? So the current can only flow one direction?
There's usually 3 or 4 in the past, you already know.
The current can only flow one direction?
Yes.
So you only get half the way? because
Right,
the other
why is it only
the
going
way-
half the direction?
The other half the way is flowing the other
Yeah,
direction.
what's in here that makes it go only half the time? Later on, we'll talk about something called diode. Like a
Oh,
check
okay.
valve,
Yeah,
it
yeah.
lets it go one way but not the other way. We need to find out whether this fan, when it's turned on, when it's heating the air, is behaving more like a hot wire, like the light bulb, or like a fan. How will we know? If it's spending more of its energy, effort in heating the air, then it will be more like resistive. But if it's spending more of its effort trying to move the air that is heated, it will be more of a fan. Come over here and find out if there's a big angle, then it must be more like moving the air. And if there's a little angle, it must be more heating the air.
The difference between your time.
Well, I'm ready to go home. Choose me.
Isn't it? If it is doing more work by moving the air, then it would be change in angle. But then, if it's more like the resistor, like the light bulb, it would just be getting hotter. Ready to find out? You know where zero reference is? Let's plug in a reference, be sure we remember where that is.
Number one. How do you measure?
In 5 minutes, we'll be there. Okay, there's our zero reference. You good with that? Yeah. We'll turn it on. What's it doing?
There's no angle difference.
Do not perceive an angle difference.
So it's heating.
So mostly it's heating.
So that fan doesn't really draw on.
The fan part of it doesn't take very much of the total energy.
So much
And
so
the
that you
heating
can't even see it on the
It's
screen.
mostly a heater. Sounds noisy, but it's mostly a heater. It is warm, right?
Yeah.
Does heat. You did it. Oh, I have one more thing to go along with this, which is not part of the instructions. I have to have something. I have another one of those little Christmas
I don't know
lights,
what all you guys are writing.
3-volt lights. I have it connected to a generator. It used to be on my bicycle lots of years ago. It's an old kind of thing. I'm gonna spin this thing and get the light to come on.
No way.
Not very well, I'm not. I'm gonna try it though. Okay, look closely, see if you see the light.
There it goes.
Okay, it takes a little effort to get that working, doesn't it? Okay, so nowadays you have more efficient generators. So let's say there's a
We got away
generator.
from hamsters in a wheel.
Let's say there's a generator on your bicycle and you're gonna pedal. Keep this light globe bright. That's gonna take a little effort, right? 100 watts, you're gonna keep it full bright for 1 hour. What does Rocky Mountain Power call that, when you keep this 100-watt bulb off 1 hour? It's 0.1 kilowatt hours? Okay. Suppose I have you pedal this thing then for 10 hours, because I need to have the light. I'm working at nighttime, it's winter time, and I need to be able to see, and so I've hired you to pedal and keep this light bright so that I can do my work.
It's not worth it.
Come
You're
on.
probably gonna
He's
want to
like,
pay me
come
for
on.
1 kilowatt hour and it's.
Yes, how much
it's
is
not
that?
worth it.
How much is a kilowatt hour?
What is it,
Like 10 cents.
8 cents and, yeah.
Yeah, 8 or 10
9
cents. So about a dime to keep it on for 10 hours, so it would have been 1 penny for the first hour. I suggest you continue being mechanical engineer or whatever and get paid for that job rather than keep my light on. And be grateful for Rocky Mountain and what they do for you, because to do it on your own. it's
They
pretty
probably
tough.
have a lot of hamsters.
And they don't pay very much.
Years that they're saving from this.